Welcome to the Deep Dive. Today we're embarking on a journey into a source that, well, it might seem a bit technical at first glance, but trust us, it's packed with fascinating stuff. We're looking at the book Fuel and Processing Terms. And forget just dry definitions. Our mission here is to pull out the really compelling nuggets,
Right.
to give you a real feel for the surprisingly complex world of fuels and how we actually get them ready to use. Think of it as your fast track to being genuinely informed without needing a PhD in chemical engineering.
Exactly. And what's really striking about this source is, well, it's sheer scope.
Yeah.
When you hear fuel, you probably think about, I don't know, gasoline for your car, right?
Right.
But this book just broadens that perspective massively. It starts with the absolute basics. What even is a fuel? What are the different kinds of gases? And then it really dives into historical technologies, the complex world of chemical processes, and even the science behind fire itself.
And it's not just abstract theory, is it? This book is full of practical details in tables. I mean, everything from the atomic level of carbon
Yeah, the nitty-gritty.
to fractional distillation, those tiny molecular sieves, flashpoints for different materials, even water properties and air pressure at altitude.
It's really comprehensive.
And for people who like the real deep cuts, there's bonus stuff too, like old diagrams of distillate burners and a simplified wood gas generator design from way back.
And, it's worth saying, whether you work in this field and maybe need a quick refresher, or you're just curious about how things work,
Right.
there's definitely something valuable in this deep dive for you. We're going to try and connect these terms and processes to the bigger picture. Explain not just what they are, but why they matter.
Absolutely. And we'll highlight some genuinely surprising things. Like, have you ever really thought about where the fuels we use every day originally came from?
Probably not in detail.
Or the incredibly intricate steps involved in getting them ready? Well, get set, because that's what we're exploring. Okay, let's unpack this. The book kicks off with an element that's just fundamental to so many fuels: carbon.
Indeed. Carbon is so central it gets its own big section, and for good reason. What's really interesting is how the book doesn't just treat carbon as, like, one single thing.
Okay.
It breaks it down into its various forms, some you might not hear about much.
Like what, specifically?
Well, it starts with atomic carbon, just a single atom. Describes it as incredibly reactive, very short-lived.
So it doesn't hang around.
Not at all. It wants to bond immediately, maybe grabbing oxygen to make carbon monoxide or formaldehyde. Then there's diatomic carbon, C2.
Two carbons together.
Yep, but it only exists as a gas at really high temperatures. We're talking over 3,600 degrees Celsius.
Fine.
And interestingly, it's actually part of those blue flames you see when hydrocarbons burn. Makes you think what's really going on in a simple flame.
You're right. Who knew flames had such exotic ingredients? And it doesn't start there, right? There's tricarbon, too.
Yes, tricarbon C3, another short-lived gas, also colorless.
And what's its significance?
It's seen as a precursor to soot, sort of like the first building block of that black stuff you get from incomplete burning.
Okay.
The book even briefly mentions larger ones like butt carbon, pent carbon, hexacarbon, but doesn't go deep on those.
Okay, so these are very temporary forms. What about the carbon that's more stable, the stuff we can actually, hold, elemental carbon?
Right. The book gives a solid rundown of its basic properties, atomic number 6, atomic weight, density, that super high sublimation point where it goes straight from solid to gas. It also lists electronegativity, how strongly it pulls electrons and ionization energies, which is the energy needed to remove its electrons. Even the van der Waals radius, its sort of effective size.
And it's bonding. Carbon's famous for making all sorts of connections.
Exactly. It highlights covalent bonds where atoms share electrons, and specifically the different lengths for single, double, and triple bonds between carbon atoms.
Those lengths matter.
Oh, hugely. Those tiny differences dictate the shape and behavior of the molecules they form. It's these basics that let carbon create such a massive variety of substances.
Okay, this is where it gets really interesting for me. The book stresses how carbon and its compounds are the basis for almost all life on Earth. It even slips in that note about except silicon-based life, which always gets your mind wandering.
It's a crucial point. Carbon's unique knack for forming stable bonds with itself and so many other elements is what makes organic chemistry and life as we know it possible.
Right.
It also mentions its resistance to oxidation under normal conditions, which is why, charcoal doesn't just burst into flames in your garage.
Good point. Speaking of lumps, the book then talks about mineral carbon. Sounds a bit different from the pure element.
Yeah, mineral carbon is mostly carbon, but it also has silica, that's silicon and oxygen. It's described as odorless, tasteless, pretty soft on the Mohs hardness scale, like 1 or 2, sublimes at a slightly higher temperature than pure carbon.
It has other names.
Loads of them. Black lead, plumbago, and the most common one, graphite.
Graphite, like in pencils.
Exactly. And the book even breaks down the types of graphite: crystalline flake, amorphous, lump, pyrolytic graphite, even graphite fiber, which is key for strong, light, modern materials.
Wow.
There's even cliftonite, a type found in meteorites.
Talk about cosmic carbon.
Carbon really is everywhere. Now, isotopes, I know they're different forms of an element, but the list here is kind of nuts. 8C up to 23C.
Yeah, the vast majority are super unstable, lasting fractions of a second before they decay.
Okay.
But the book rightly flags the important ones. The stable isotopes, carbon-12 and carbon-13, which are most of the carbon out there. And of course, the radioactive one, carbon-14.
Ah, carbon-14, the dating isotope, for figuring out how old ancient things are. Precisely. The book explains the nitrogen-14, carbon-14 cycle. Basically, cosmic rays hit nitrogen in the upper atmosphere, tuning it into carbon-14.
Okay.
The C14 gets into living things. When they die, it decays back to nitrogen-14 at a known rate.
Right.
That constant cycle in living things is the basis for radiocarbon dating, a huge breakthrough by Willard Libby.
Okay, let's just make sure I've got this. While something's alive, it takes in carbon, including a tiny bit of C14.
Constantly.
Then it dies, stops taking in carbon, but the C14 it has starts decaying, like a clock ticking down.
Exactly.
So by measuring how much C14 is left, scientists can estimate how long ago it died.
That's the core idea. The book mentions the half-life, about 5,730 years, for half of it to decay. And dates are usually given as before present, with 1950 AD as the 0 point.
But it's not perfect, right? There have to be limitations.
Oh, absolutely. The book lists potential error sources. Contamination of the sample is one.
Yeah.
Fluctuations in Earth's magnetic field or cosmic rays over time that affects how much C14 was made in the first place. Variations in atmospheric C14 levels.
So how do they account for that?
Well, calibration is key. Using things like dendrochronology tree ring dating helps fine-tune the C14 dates.
Ah, clever.
And the book even touches on criticisms, like assumptions about very old rocks or past radioactive levels. It's a good reminder that even solid science has nuances and gets refined.
It really is. Now, the book mentions the old inorganic versus organic carbon distinction. I vaguely remember that from school.
Yeah, that's a 19th century idea. Scientists used to think organic carbon compounds only came from living things, inorganic from minerals.
And that organic needed hydrogen.
That was part of the old thinking, yeah. But the book rightly points out our modern view. These types can be converted back and forth chemically. The real difference now is structure, especially carbon-hydrogen bonds in most organics, not the source.
That makes way more sense. Okay, let's get to some actual molecules. Carbon monoxide, CO, the dangerous one.
Yes, and the book explains why. It's got this unique, very strong triple bond between carbon and oxygen.
Okay.
It's colorless, odorless, tasteless, which is what makes it so insidious you can't easily detect it. Slightly less dense than air, too.
And the danger is the toxicity.
Primarily, hemoglobin in our blood carries oxygen, right?
Right.
Well, hemoglobin grabs onto CO about 200 times more strongly than oxygen. So it basically blocks oxygen transport, starving your tissues.
That's why CO poisoning is so scary. You don't realize it's happening. The book gives some stark numbers, too, typical levels from natural air up to wood fire exhaust.
It does, and it classifies CO as an oxocarbon, just an oxide of carbon and a ligand, meaning it binds to metal atoms, like the iron in hemoglobin.
Okay.
It also mentions the carbonyl group, that carbon-oxygen double bond structure, which is key to its reactivity.
Got it. Next, carbon dioxide, CO2. Less immediately toxic in small doses, but obviously a huge topic today.
Right. CO2 has a central carbon double bonded to 2 oxygens. Also colorless, odorless normally. Dissolves in water to make carbonic acid, that's the fizz in soda. The book gives its precise masses, densities as gas and liquid, boiling melting points. Even typical valences, how many bonds atoms form, and total valence electrons, explaining the bonding.
And where does CO2 come from? Seems like everywhere.
Pretty much. Aerobic organisms, us included, breathe it out.
Respiration.
Natural decay of organic stuff, fermentation by yeast, and combustion burning almost any organic material. Wood, peat, fossil fuels.
Right.
It even notes conditions to liquefy it, how it breaks down at high temps, and lists common names like dry ice for solid CO2.
Now, total inorganic carbon, PIC or DIC, That sounds like it brings a few things together.
Yeah, ticker DIC is basically the sum of all dissolved inorganic carbon forms in water. So dissolved CO2 gas, carbonic acid, bicarbonate ions, carbonate ions.
Okay.
The book explains how the balance between these affects water pH. Carbonic acid makes it more acidic.
Got it. Then some basic chemistry. Simple carbon combustion and carbothermic reactions.
Simple combustion is just C plus O2 gives CO2, releases energy.
Standard burning.
Carbothermic reactions are different. Carbon acts as a reducing agent. At high temps, it can steal oxygen from metal oxides, leaving the pure metal. Often makes CO or CO2 as byproduct.
Carbon fission and fusion sound.
Yeah.
Nuclear.
They are. Fission splits the nucleus, fusion joins nuclei. Both release massive energy, EMMC hot.
Right.
Book notes not much public info on controlled fission on Earth, but talks about fusion in stars.
Ah, yes. The stellar carbon cycle. That's some serious chemistry.
It really is. Inside stars, at incredible temperatures and pressures, carbon fusion is huge. The book outlines the CNO cycle, carbon, nitrogen, oxygen.
CNO.
Yeah. Carbon-12 acts like a catalyst. It captures protons, alpha particles, and a series of nuclear reactions, makes nitrogen, oxygen isotopes, and releases enormous energy. Powers the star.
So carbon isn't just fuel here. It helps power the stars themselves. What a versatile element. Okay, back down to Earth, literally, with the Earth's carbon cycle.
Exactly. The natural circulation of carbon through the biosphere, living things, geosphere, rocks, soil, hydrosphere, water, and atmosphere, air.
And the processes involved.
Things like carbonification, the slow process turning organic matter into coal and oil, respiration, decomposition of dead stuff, and photosynthesis by plants pulling CO2 out of the air.
To understand the atmosphere's part, the book breaks down the gases. Atmosphere, stratosphere, troposphere, mostly nitrogen and oxygen, but those trace gases matter.
Precisely, which leads to greenhouse gases. The book defines them as gases that absorb and emit infrared radiation.
Trapping heat.
Like a greenhouse roof, yeah. Traps heat in the atmosphere. Lists the main ones. Water vapor, CO2, methane, nitrous oxide, ozone.
And this heat trapping is the greenhouse effect. Natural keeps Earth livable.
Right.
Then it touches on global warming, the idea that more greenhouse gases, especially CO2, trap too much heat, raising Earth's average temperature since the late 1800s.
It presents it carefully, linking it to increased concentrations and the scientific understanding that this likely causes climate changes. Notes the natural and human sources, too. It's complex.
It is complex, and climate change is the broader term for those long-term shifts in temperature and weather patterns linked to global warming.
Huh. Okay, carbon suboxide. Sounds weird.
It's pretty unique. C3O2. Linear structure, 3 carbons, 2 oxygens, linked by 4 double bonds in a row. A type of cumulene. Colorless gas, pungent smell. Can form in trace amounts from carbon monoxide processes.
Anoxocarbon is just any compound with only carbon and oxygen.
That's the gist. And carbon burning here loops back to stars, creating heavier elements by fusing carbon nuclei.
Okay, slight shift. Complete versus incomplete combustion. Seems straightforward.
Complete combustion needs plenty of oxygen. Carbon goes fully to CO2, hydrogen to water, maximum energy release.
Ideal burning.
Incomplete combustion happens with too little oxygen. You get byproducts like CO.
Which we know is bad.
And tiny unburnt carbon particles, soot, also called carbon black or lamp black. So soot is just unburnt carbon bits. And charcoal is impure carbon made by heating organic stuff without much oxygen.
Exactly. Destructive distillation drives off water and volatiles, leaving mostly carbon. Activated carbon, or charcoal, is processed further for huge surface area.
Making it super absorbent.
Which is why it's used in filters, purifiers, good at grabbing onto stuff.
And finally, in this carbon deep dive, Q-carbon and carbonize.
Q-carbon is fascinating. A newer form made by rapidly cooling molten carbon. It's electroconductive, ferromagnetic, harder than diamond.
Wow.
And carbonize just means turning something into carbon, usually by heating without air. Okay, let's move from this fundamental element to a material packed with it.
Coal. Yeah, coal.
Yeah.
A classic fossil fuel. Book calls it a carbonaceous rock used as fuel. And makes the point.
Yeah.
It's the carbon compounds inside that burn.
Right.
Notes quality varies a lot by location, too.
It does. And interestingly, briefly mentions sustainable coal, though without much detail on what that actually means. Then it gets into coal band grading. Explains the 4 main visual types in a lump of coal. Durain, fusane, clarane, vitrain. Different textures, looks, composition. Also mentions coal petrography using microscopes and light reflection to classify it further.
It's like a whole science of just looking at coal. Bright coal, dull coal, block coal, splint coal. The list is long.
Indeed. Each term, like V-train or clarane, means specific chemical and physical traits. Bone coal has high ash. Candle coal, rich in spores, burned brightly for candles once.
Yeah.
Fusane is often fragile bands in the seam, really shows coal isn't just coal.
Right. And then, seemingly out of nowhere, sphagnum moss? What's that doing here?
But it's a key ecological link. Sphagnum is the main stuff in peat.
Peat.
Partially decayed plants. It's basically a precursor of coal over geologic time. Peat bogs, mires, swamps, marshes, they trap and store huge amounts of carbon.
How did the moss do that?
It holds amazing amounts of water. It's highly acidic, which slows decay way down, plus compounds in its cell walls resist decay. Unique growth patterns, too.
So these bogs are natural carbon sinks. But the book says the carbon isn't locked away forever.
Exactly. If peatlands dry out, naturally or due to us, the organic matter decays faster, releasing CO2.
Okay.
Burning peat releases it too. Even water flowing through bogs carries dissolved carbon. It shows even natural storage is part of a dynamic cycle.
And then the less pleasant side, coal dust.
Yes, the fine particles made during mining, transport, handling. The book stresses the danger. If this dust hangs in the air in a confined space and ignites,
Big trouble.
incredibly dangerous explosions. Initial combustion heats and ignites nearby particles, chain reaction, rapid flame spread, massive pressure buildup.
Primary and secondary explosions.
Right. Primary at ignition, secondary, often worse as the pressure wave kicks up more dust. Mentions deflagration, subsonic, and detonation, supersonic.
Terrifying. And beyond explosions, the long-term health risk.
Yeah.
Black lung disease.
Also called coal workers' pneumoconiosis, anthracosis, or silicosis if silica is present. Breathing in fine coal dust over time causes inflammation, scarring, debilitating, potentially fatal lung diseases, a stark reminder of the human costs sometimes tied to fossil fuels.
Absolutely. And then just a quick mention of blue coal, just a brand name with blue powder added. Okay, moving to another huge category, hydrocarbons. Chains and rings of carbon and hydrogen.
The foundation of so many fuels we use, the book immediately splits them. Aromatic hydrocarbons.
The ring structures.
Yeah, stable rings, alternating single-double bonds, sigma and pi, can be monocyclic, one ring, or polycyclic, many,
Sure.
versus aliphatic hydrocarbons. No aromatic rings, only single bonds, sigma, can be saturated, alkanous alkenes with double, triple bonds. Chains can be straight, branched, or even non-aromatic rings.
And then terms for parts of these molecules.
Yeah.
Arylene, aryl, alkyl, like building blocks.
Essentially, yeah. Functional groups are radicals. Bits you attach to a main chain or ring, changing its properties. Arylene and aryl come from aromatics, alkyl from aliphatics, like molecular Lego pieces.
And the basic aliphatic types, alkenes, alkenes, alkynes. Definitely remember those from chemistry.
Alkenes. Saturated, only single CC bonds. Formula CnH2n plus 2. Alkenes, unsaturated, at least one CC double bond, more reactive. Alkenes, unsaturated, at least one CC triple bond.
Now we get into familiar fuels. Petroleum, rock oil, crude oil, gas. Almost a cascade of terms.
Petroleum, from Latin, rock oil, is the broad term for natural liquid hydrocarbon mixtures. Rock oil, or naphtha, is liquid found in or distilled from petroleum or coal tar.
Right.
Oil here is liquid petroleum, natural or refined. Crude oil is specifically the unrefined stuff straight from the ground. Fossil oil.
And gas.
Just any flammable hydrocarbon mixture that's a gas at normal conditions.
And more specific fuel types. Gasoline oil, gasoline, petrol.
Gasoline oil was an old brand, mostly for lighting. Gasoline is the refined petroleum liquid for car engines.
What we use daily.
Petrol, British term for gasoline, refers to petroleum with mainly aliphatic hydrocarbons, linked to octane rating for engine knock resistance.
Syncrude, pitch, bitumen, asphalt, tar. These sound heavier, stickier.
Exactly. Syncrude, synthetic crude, is upgraded bitumen. Bitumen is that super thick, almost solid residue from distilling crude oil and tar.
Okay.
Pitch, bitumen, asphalt are all related dark, sticky, viscous stuff. Tar is similar, black, viscous, from wood, peat, or coal tar, specifically from coal distillation.
And kerosene. Hugely important for lamps before electricity.
Indeed. Invented by Abraham Gessner from processing carbonaceous rock oils, later made efficiently from petroleum distillation.
Key properties.
Book lists: flashpoint, lowest temp for ignitable vapor. Auto-ignition temp, ignites spontaneously. Heat value, energy released. Also common names: paraffin, lamp oil.
Now, gases found with oil wells. Associated gas and non-associated gas.
Associated gas is found dissolved in crude oil or as a gas cap above it. Typically methane, ethane, propane, butane, pentane, plus nitrogen, CO2.
But not associated.
Comes from wells, mainly producing gas and or condensate. light liquid hydrocarbons, not much crude oil.
Sweet gas versus sour gas sounds like quality terms.
They are. Sweet gas has low hydrogen sulfide, H2S, that corrosive, toxic, rotten eggs smell gas. Sour gas has high H2S, harder and costlier to process.
And coal bed gas, or methane gas, trapped in coal seams.
Exactly. Trapped in coal pores, dissolved in water in the seams, or free gas in fractures, sometimes called coal seam gas.
Then methane itself gets more detail.
Colorless, odorless, aliphatic hydrocarbon gas. Main natural source is anaerobic decomposition by methanogen bacteria, think swamps, landfills.
And methane clathrates, those icy structures trapping methane.
Yeah, clathrate hydrates. Methane molecules caged in a water crystal lattice, found on ocean floors, Antarctic permafrost, sometimes called fire ice, ignite them, the methane burns.
Raw natural gas versus pure natural gas.
Yeah.
So raw is straight from the ground. Pure is processed for delivery.
Precisely. Raw gas is a mix. Methane plus ethane, butane, propane, CO2, nitrogen, H2S, depends on the source.
Impurity.
Pure natural gas pipeline quality. Dry natural gas has had heavier hydrocarbons, water, impurities removed to meet standards. Book even mentions U.S. standards for H2S, heating value.
And natural gas liquids are the valuable byproducts separated out propane, butane, used as fuels themselves. The book lists tons of potential impurities in raw gas, too. Some nasty ones like mercury, radon.
Indeed. Processing aims to remove those for safety and efficiency. Condensate is another byproduct. Light liquid hydrocarbons, butane, pentane, hexane, that condense out, used as fuel or solvent.
And liquefied gas, LNG and LPG.
Liquefied gas is just gas turned liquid, usually by cooling or pressure. Liquefied natural gas, LNG, is natural gas cooled way down, minus 162 degrees C to liquid. Reduces volume hugely, easier for ship transport.
Right.
Liquefied petroleum gas, LPG, is usually propane and butane mix. Liquefies at moderate pressure. Used for heating, cooking, vehicles, autogas.
The list keeps going. Diesel fuel, biodiesel, butanol fuel.
Diesel fuel, refined petroleum for compression ignition engines, biodiesel. Renewable fuel from vegetable oils, animal fats reacted with alcohol, transesterification. Butanol fuel, alcohol, either from petroleum or biologically. Fermentation of biomass, then called biobutanol.
More specialized types. Acid gas, shale gas, biogas, substitute natural gas.
Acid gas, general term for acidic gases like CO2, H2S, and natural gas. Shale gas soil, trapped in low permeability shale rock, needs techniques like fracking. Biogas, methane CO2 mixed from anaerobic digestion, landfills, wastewater. Substitute natural gas, SNG. Synthetic gas from coal or biomass, similar energy to natural gas. Wet gas just means natural gas with lots of liquid hydrocarbons. HCNG is compressed natural gas plus hydrogen.
Syngas water gas, carbureted water gas. Sound like older tech.
Syngas synthesis gas. CO, H2, maybe CO2 mix. From gasifying coal, biomass, etc. Water gas. Specific syngas from steam over hot carbon. Coke, mostly CO plus H2.
Right.
Carbureted water gas. Water gas enriched by passing through hot oil, boosts heating value, brightness. Book mentions semi-water gas, blue water gas, too, variations.
Pyrolyzed oils, bioasphalt, coal gas. The variety is amazing.
Pyrolyzed oils, bio-oil, bio-crude. Complex liquids from heating biomass, wood, algae without oxygen pyrolysis. Bioasphalt, renewable alternative to petroleum asphalt from biosources.
And coal gas.
Coal gas, town gas, synthesis gas. H2 plus CO from heating coal with steam. Illuminating gas was just coal gas used for lighting before electricity.
And wood gas, like from the generator design in the book.
Exactly. Heating wood organic stuff with limited air gasification makes syngas and CO, H2. Producer gas, similar. Air over hot coal coke, N2 plus CO. Mond gas, another coal gas type, N2, H2CO2, COCH4. Fuel gas is just a general term for any gas fuel.
Finally, acetylene and related terms. Unique hydrocarbon.
Acetylene, C2H2, triple bond, burns super hot in oxygen, great for welding, cutting, used for lighting too once. Made from calcium carbide plus water.
Acetylene.
Compounds formed when acetylene reacts with metals. Acetylene torch uses acetylene plus oxygen. Acetylene black is carbon black from decomposing acetylene.
And still more gases listed.
Landfill gas, green diesel, biofuel gasoline, solid biofuel, even fungi fuel really covers the waterfront of fuels.
It certainly does. Okay, after that whirlwind, let's hit additional fuels beyond coal and oil, starting with alcohols.
Alcohols, organic compounds with one or more hydroxyl OH groups on a carbon, many made by fermentation microbes turning sugars into alcohol. Common ones. Ethanol, propanol, butanol. Used as fuels, solvents.
Ethanol gets more detail. Makes sense. Big biofuel.
Yep. Production mainly via fermentation, corn, sugarcane. Key properties. Colorless, volatile liquid, burns clean blue, almost smokeless. Great solvent.
And used in V2 rockets.
Historically, yes. A component in their fuel during WWII. Surprising tidbit.
Defo. Then flashpoint, crucial for safety.
Flashpoint.
Yeah.
Lowest temp, a liquid gives off enough vapor to ignite with air near the surface. Book gives values for ethanol water mixes and pure ethanol. Shows how water affects climbability.
Then a whole catalog of alcohols.
Yeah.
Straight chain ones from methanol up to triacotanol, 30 carbons. Like a mini chemistry text.
It's comprehensive. Shows the huge number of alcohols. Lists other primary, secondary, tertiary alcohols, too. Highlights the structural diversity. Many used as fuels, solvents, chemical starting points.
Now, pinch gas and blow gas sound like relics.
Fascinating historical examples. Pinch gas, 19th century Julius Pinch. Compressed gas, not liquefied. From distilling naphtha, gas oil, often enriched with methane for brightness.
Used for
Illumination mainly. Railway carriages, lighthouses, better than oil lamps then. Portable gas.
kind of a precursor to modern bottled gas.
In a way, yeah. Portable, efficient for its time where pipes weren't an option. Then blow gas, early 20th century, Herman Blow. More advanced liquefied gas.
How's it made?
Carefully blended light fractions of mineral oil, gasoline, plus permanent gases separated by an aniline column. Stored liquid under high pressure, vaporized for use. Used in engines domestic, industrial. Book details its production, global spread, engine use. Lists features. High energy content, specific gravity, composition, non-toxic, no CO, unlike some earlier gas fuels. Provides other mixture examples, heat outputs, even a production schematic, a real glimpse into early 20th century gas tech ingenuity. Developing safer, better fuels.
Definitely shows how far we've come and how those early steps paved the way. Okay, processing and related technologies, how raw fuels become usable energy. Starts super basic. Pot, water kettle, electric kettle.
Sometimes the simple tools are the foundation, just basic ways to heat water. Pot uses direct heat, kettles use elements to boil water.
Then the retort sounds like alchemy.
Has that feel. A sealed vessel, often flask with bent neck. Heat stuff, collect volatile vapors that condense elsewhere. Used for recording shale oil gas, general airtight chemical reactions.
And superheated water above 100 degrees Celsius. Counterintuitive.
Seems so, but possible under pressure, prevents boiling. Steam can also be superheated above its saturation point.
How do its properties change?
Book notes lower surface tension, viscosity, higher self-ionization, more dissociation into ions.
Which leads to the steam digester, Papin's invention. Early pressure cooker.
Exactly. Late 17th century, airtight pot, heated water inside, pressure builds, water temp goes way above 100 degrees, seal it. Cooks faster.
Why faster?
Chemical reactions like food breakdowns speed up at higher temps. Papin added a crucial safety valve too, prevented explosions.
And he worked on steam engines later?
Yeah, shows his progression thinking about steam power. Flash boiler, rapidly heats small water amounts in a coil, can superheat if sealed. Canning retorts, pressure vessels for sterilizing canned food. Makes sense. Links back to Papin. Pressurized steam for sterilization. Retort sterilization lists various methods using steam or hot water under pressure. All examples of using controlled heat and pressure for specific outcomes, food prep, preservation, industrial processes.
Yeah, separating mixtures, still, and distillation.
Distillation. Fundamental separation based on different volatilities, how easily things evaporate. A still is the apparatus. Heat liquid mix, create vapors, cool vapors to condense back to liquid, separates more volatile from less volatile.
Purification versus fractionation.
Purification rectification aims to concentrate one substance. Fuel processing fractionation separates complex mixes like crude oil into different products.
Distillate is the collected liquid. Rectification is repeated distillation for higher purity. Alembic sounds like an older still.
Older design, yeah. Typically 2 retorts connected by a tube, maybe a spout. Fractionation, as mentioned, is separating by boiling points, phase changes at specific temps, hydrocarbon dew point, temp pressure where hydrocarbon vapors condense from gas.
And the fractional distillation column for crude oil, the refinery workhorse?
Absolutely. Book details it. Heat crude in furnace, vaporize components, feed hot vapor mix into bottom of tall column.
Temperature gradient.
Hotter at bottom, cooler at top. Vapors rise, cool, condense back to liquid at different heights based on boiling points. Bubble caps, separation trays help collect fractions, gasoline, naphtha, kerosene, diesel, heavy gas oil, residue at different levels, also called petroleum fractionation.
Aniline column is specific for aniline steam separation. Uses condensation, gravity, heat.
Specialized gear, yeah. Cryogenic processing plants use extreme cold to condense and separate natural gas liquids.
Also called striping plants.
Right. Very low temps condense heavier hydrocarbons, ethane, propane, butane, out of natural gas. Then fractional distillation at warmer temps separates those liquids.
Gasification key for turning solids into gas fuel.
It is. Book outline stages. Drying moisture. Pyrolysis to volatilization. Heat without oxygen, made a gas, char. Combustion. Volatilization plus limited oxygen, heat, CO2. Reduction, hot char plus steam, CO2 as syngas, H2 plus CO.
And a gasifier is a reactor. Many types listed.
Updraft, downdraft, cross-draft, fluidized bed, plasma. Each with pros and cons for efficiency, feedstock type, syngas quality. Ongoing innovation here.
Then hydrogen from coal via gasification. Many approaches listed.
Several techs. Steam iron, steam oxygen, suspension, fluidized bed gasifiers, specific processes like CO2 acceptor, BIGAS, synthane, Lurgy, Lane, sponge iron reactor cycles.
Hydrogasification.
Reacting coal with high-pressure hydrogen to make methane directly, and hydrogenate just means react with hydrogen.
Water-gas shift reaction seems crucial for hydrogen production.
Absolutely. Reversible reaction, CO plus H2O equals CO2 plus H2. Exergonic, releases heat. Book mentions mechanisms, Langmuir-Hinshelwood, redox associative. Reverse reaction is also important sometimes.
Mentions methane oxidation, methanol synthesis using syngas to make other chemicals fuels. Low process sounds older for water gas.
Earlier method, steam over burning coal enriched with coal oil, blue water gas, or gas with yellow flame.
Electrochemical hydrogen compressors, modern, solid state.
Potentially more efficient. Use proton exchange membrane, PEM, like fuel cells. Electric current moves H plus ions through membrane, compressing gas without moving parts. Book notes, DOE grant interest, important for hydrogen tech.
Joule-Thomson effect. Gas expansion cools it. Used in throttling process for cooling.
Precisely. Real gas expands rapidly through valve plug, no heat exchange. Under right conditions, it cools. Key for refrigeration, AC, thermal expansion, heat pumps.
Cascade liquefying process and Hampson-Lind's cycle cooler for liquefying gases like N2O2.
Cascade uses series of refrigerants with lower boiling points. Hampson-Lind, regenerative cycle. Compress gas, remove heat, cool via heat exchanger, expand through valve, Joule-Thomson cooling. Cooled gas pre-cools incoming gas. Repeat until liquid.
Lind process similar. Charles and Gay-Lussac's law relates gas volume and temp. Siemens cycle, another cooling cycle.
All key thermoprinciples processes for low temps, liquefaction, cryogenics, expansion, turbinate, turbo expander. High pressure gas expands, does work, cools down.
Claude process. Named after George's Claude.
Uses isenthalpic, no heat exchange, and isentropic, constant entropy expansion in a work device, piston turbine. Gas does work, cools efficiently, followed by heat exchanger. Repeat to liquefy. Claude also worked on ocean thermal energy conversion.
Book explains general conditions for liquefaction. Cool to saturated vapor, pressure overcomes vapor tension. Air example given. Boiling point. Vapor pressure equals surrounding pressure. Calefaction just means heating. Side note on historical caulking with heated pine resin.
Practical use of heating to change properties. Light and frost phenomenon. Liquid on very hot surface forms, insulating vapor layer doesn't boil instantly. Fascinating heat transfer quirk.
Monge-Clouet liquefaction. Early, simple method. Sulfurous acid gas through U-tube in salt ice mix for cooling.
Basic, but showed the principle. Clausius, Clapeyron, and Antoine equations estimate vapor pressure versus temp. Antoine, more accurate, uses coefficients. Dalton's law. Total pressure of ideal gas mix is sum of partial pressures. Adiabatic demagnetization magnetocaloric effect. Advanced technique for ultra-low temps using changing magnetic fields.
These are essential thermophysical chemistry concepts for gas-liquid behavior, phase changes, temp control.
Absolutely critical.
The vortex tube sounds like sci-fi. Compressed air in, hot air out one end, cold out the other.
Intriguing device. Exact physics debated. Theories involve temperature gradients from complex swirling air, clockwise counterclockwise streams separating hot-cold. Niche use for localized cooling heating. Book briefly mentions Victor Schauberger's unconventional implosion ideas, though not directly linked.
Then redefinitions. Gasification, carbon to COH2 fuel, regasification, LNG back to gas. Field processing, gathering systems, centralized plants, straddle plants infrastructure for gas from well to user.
The whole journey. Raw gas field processing, gathering pipes, centralized plant purification, maybe straddle plant, more purity.
Distillation versus destructive distillation revisited. Separation by boiling point versus decomposition by heat without air with reagents. High versus low temp deconstruction based on temp range. In situ retorting. Heating oil shale underground.
Right. Furnaces, heating fluids, incinerators, burning waste. Line heaters prevent freezing, improve separation in pipelines, all apply heat differently. Then a rapid fire list. Hydrogenate, dehydrogenate, cracking, hydrocracking, fermentation, ferment yeast, bacterium conversion, microbial fuel cell, bacterial nanowires.
A whirlwind of chemical biological transformations for fuels chemicals.
Shows the diverse methods used. Hydrogen compressor, compressed hydrogen revisited, high pressure, low auto ignition temp. Liquid hydrogen, cryogenic, very low boiling point. Ionic liquids, low temp salt solvents. Compressor types, positive displacement versus dynamic displacement.
Positive displacement compressors explained. Trap gas, reduce volume, increase pressure, piston cylinder. Analogies to heat engines, pumps, fire piston. Rapid air compression ignites tinder. Ionic compressors use ionic liquid as piston. Absorption, surface film versus absorption intake into material.
Key differences in gas-liquid interaction. Nitrogen rejection units, pervaporation, oxygen concentrators, air separation techs for purifying, separating gas mixes, air, natural gas.
Chromatography, electrophoresis, analytical separation techniques. Chemical synthesis, cracking, reforming, fundamental for making modifying fuels. Reformers, steam reforming, crucial for making hydrogen from hydrocarbons.
Plasma reforming gasification use high-energy plasma for transformations. H2 from hydrocarbons, waste to syngas. Oxidation, partial oxidation, electron loss, limited oxygen reaction. Autothermal reforming, self-heating processes.
Aminas, amine, treating, scrubbing remove acidic gases, H2SCO2. Amine reboilers regenerate the amine solution. Molecular sieves, materials with precise pores to separate molecules by size shape.
Useful for drying gas, separating isomers. Dehydrators, drying agents remove water. Separators. Pressure vessels, separating gas liquid by density. Heated separators use warm water bath to help separate oil-water emulsions in crude oil.
Oil-water emulsions are a challenge. Oleophilic, oil-loving, silane, phthalic anhydrides, oil-sorbent sponge absorb oil spills.
Slagging gasification, high temp, melts ash to slag. Benefits for waste, destroying hydrocarbons. Rarefication vacuum, reduced density pressure. Purified compressed air needed industrially, medically. Carbonization, decarburization, control metal carbon content.
Then polymers, monomers, copolymers, grasped, block. Hydrolysis breaks bonds with water. Saccharides, polysaccharides are carbs. Ground substance, microfibrils, matrix describe plant cell wall structure.
Leads to saccharification, breaking complex polysaccharides to simple sugars, often from lignocellulose. Biorefineries process biomass into products like cellulosic ethanol via cellulolysis fermentation distillation or gasification catalysis.
Vacuum molecular distillation use reduced pressure for lower temp separation. Molecular uses high vacuum. Refractory materials withstand high temps. Induction furnaces use electromagnetic heat.
Fluidization makes solid particles act like fluid via gas-liquid flow. Many types. Fixed bed, bubbling, fast fluidized bed. Used in fluidized bed boilers, efficient combustion. Separation combustion, often with limestone for pollutant capture.
And finally, pneumatic tubes. Transport via pressurized vacuum tubes. Boilers, thermic fluid heaters. Steam indirect heat. Distillate fuel burners use specific fuels. Metal water explosions, potential violent reactions. Phew, that was intense.
It was a deep dive into a massive range of tech, but still got refrigerants and fire-related terms.
Right, you are. Let's hit refrigerant stuff for chilling things.
Refrigerants. Substances that absorb heat one place, release it elsewhere, often phase change in a cycle for cooling. Cryogenics, extremely low temps. Cryogenics, study use of low temps. Cryopreservation, preserving tissue at very low temps, a negative 80 to negative 200 degrees C.
Cryogen.
Liquid refrigerant, boiling below, negative 150 degrees C. Inert gas, flammable gas, oxygen under specific conditions, subcool. Liquid refrigerant cooled below its saturation temp.
Halocarbon refrigerants, like Freon mentioned. Azeotropic versus zeotropic.
Azeotropic, fixed boiling point mix, constant composition liquid vapor, can't separate by distillation. Zeotropic, composition differs liquid vapor during phase change, separable by distillation.
Also lists inorganic refrigerants, natural water air, CO2 ammonia, SO2, and hydrocarbon refrigerants, natural, ethane, propane, butane. Eutectic point, lowest freezing point of a mixture, refrigerant brines, saltwater secondary coolants, lyophilization freeze drying, rapid freeze, vacuum dehydration sublimation. Okay, final technical bit, fire-related terms, the science of burning.
Fire, rapid chemical reaction. Fuel plus oxygen, heat, light, flame. Flame, visible burning vapor, smolder, flameless burn on solid surface, often smoky. Ignition, starting the burn. Burning, sustained reaction with ample O2. Combustion, broader term flaming or flameless, maybe limited O2 in complete products. Explosion, subsonic. Detonation, supersonic. Rapid volume increase, shock waves. Smoke, visible particles, gases, aerosol, particles and gas. Melt, solid to liquid, vapor, gas phase of normal liquid solid. Fume, condensed particulate aerosol, aerosol rapid compression, igniting aerosol mixed by rapid compression.
Key difference: flammable, flash point 37.8 degrees C, versus combustible, flash point 37.8 degrees C. Pyrolysis, decomposition by heat without oxygen, chain reaction. Self-propagating reactions, combustible can burn versus incombustible cannot. Explosive condition needs fuel, oxidizer, ignition source and right ratio. Ignition sources, static, sparks, hot surfaces, compression, high heat, flash point. Lowest temp for ignitable vapor air mix. Explosive, flammable range, concentration limits, LEL too lean below, UEL is too rich above, stale air. High CO2 in sealed room, ventilation, fresh air replacement, ventilation safety, keep combustibles 25%, LEL, specific gravity safety, gas density effects, hazard location, heavier sinks.
Damp, German for flammable gases under pressure. Mines, specific types. White damp, CO, H2S, toxins. Black damp, stive, choke damp, asphyxiant N2CO2 vapor mix. Stink damp, H2S, rotten eggs. After damp, post-explosion mix. CO2, CO, N2 toxins. Canaries, mice used for detection historically.
Finally, fuel cells, future power source.
Electrochemical devices convert chemical energy, fuel plus oxidant, to electricity via reactions. Continuous supply needed, unlike batteries. Power from electron flow anode to cathode via external circuit.
Types.
Details. Proton exchange membrane fuel cells, PEMFC. H2 plus O2 air. Solid polymer electrolyte, platinum catalyst, 80 degrees C. Separates protons, electrons, briefly mentions others. Alkaline, phosphoric acid, molten carbonate, different electrolytes, temps. Alkaline membrane, alkaline liquid fuel cells too. Reversible fuel cells, PEM type, can also do electrolysis, split water using electricity.
Well, that has been an absolutely monumental deep dive into this incredibly detailed world of fuel and processing terms. Wow.
Yeah.
From basic carbon right through to fuel cells. It's amazing how vast and connected it all is.
It really is. And hopefully this overview has, given everyone a valuable and insightful handle on this complex subject. Spark some curiosity, maybe, without being totally overwhelming.
Absolutely. And it really makes you appreciate the sheer amount of innovation throughout history in our search for energy. Think about those like niche technologies we talked about, pinch gas, the steam digester. They weren't just quirky things. They really laid the groundwork for so much we take for granted today. So here's a final thought to maybe chew on. What seemingly obscure or even historical bit of knowledge might hold a key to future energy challenges?
Interesting question.
Maybe it's worth looking back at some of those older ideas with fresh eyes, see what hidden potential might still be there. And of course, if you want to dig deeper into any of this, the book Fuel and Processing Terms is waiting. Thanks for joining us on The Deep Dive.